Hello everyone. I'm Ayush Kumar Tyagi. I am PhD student at IIT Delhi. I will be taking today's session for diffusion models, and we will be looking into the practical aspects of diffusion model. We will look into some of the demos, and then we will go back to solving few of the problems related to diffusion models. Right. Uh, so let's get started, right? So we have seen that GANs and variation autoencoders, they were good in doing the reconstruction. They were doing in exploring the latent space, right? GANs has their own issues. They were good in generated new images, but there was cases where GANs suffer from mode collapse, so generating same type of images, right? And there are many cases where the guidance, suppose a text guidance or any type of class conditional guidance was missing, right? And there are variants with conditional guidance where you can actually provide a class label where of from which you want to generate a sample images. So, uh, like there is the progress in the generative images has been uh, uh, like in this order. So earlier there were variation autoencoders GANs, which basically came around in the similar timeline. Then you move to hierarchical GANs, right? And then there was a class of models which is called as the diffusion model. So, let me just share with you a paper of the initial diffusion model. So this is the initial paper of the diffusion model. So this, in short, is also called as the DDPM, denoising diffusion probabilistic model, right? And what they are doing is they are sequentially adding noise at each time step, and in the forward process and the reverse process, they are learning how to actually denoise or predict the noise which has been added at each step, right? If you can see that uh, from x0, which is your original image, you move towards adding noise, and you add till it is completely Gaussian, right? And in the reverse process, what you do is you learn how do you what is the amount of noise you have added at each step. You predict that noise, you subtract that noise from your image, and you try to reconstruct at that each point of time. And if you do it subsequently, you will end up getting the whole image again, which is completely denoised version of your original image, right? And so the diffusion model actually works in time steps. So if there are t time steps, and it depends on how many time step you are actually looking into. So in typical cases, if you are training stable diffusion or the state of the art diffusion models, people actually look for 50 to 100 time steps, and those are generally sufficient for even for the complex cases. But you can actually try increase the number of time step, so that you can actually get maybe capture fine grained details. However, increasing the time step actually becomes makes the model more complex, and start to introduce some errors within in the reconstruction task or the denoising task, right? So uh, that actually becomes challenging. And also in term of inference, right? So more the number of steps are more uh, time you are going to take. So if you have 50 steps, suppose, right, then you might take let's say around uh, 2 to 3 seconds. If there are 100 steps, then you might take 5 seconds, right? So the number of steps actually dictate uh, how much time your model is going to take during the inference, right? So if you can see, this beta is basically noise you are actually injecting in the forward process of the diffusion, and when you are coming back in the reverse process, you are predicting what noise which was added and you subtract it from the model at each step. So this is a very interesting read. I would suggest everyone to look into the paper, and then uh, like then actually it becomes very very interesting. So um, if you actually look at the numbers, right? So let's look at the scale, how good diffusion models are. So FID is one of the metric which was used like in identifying how good that like generations were, right? So in case of conditional case where you have some class condition or text condition, so this big GAN is like a large variant of GAN, and it was state of the art at that point of time. uh, so it gets close to 14.73 FID, and this tile GAN was like getting, which is a variant of this only, right, is getting 2.67 uh, FID, right. Similarly, if you can actually look into the original, the unconditional cases, uh, this spectral normalization GAN and this SG GAN, these are close to 15.42, whereas this diffusion model is in the range of 3.17. So this actually like changed the landscape of this generative models, and like earlier people are actually finding it difficult to generate images, and now with diffusion models, this the shift has been, there has been a rapid shift. So you are able to generate very good images, and and they actually look realistic in many cases. So what they do is they have, I think this time step is 1000 for their experiment, but like it works for lesser as well. For inference time and the training time, you can actually have different time step, I guess. Because in most of the cases which I have seen, you can actually have time step of 100 or maybe 50, and then you still be able to get a good reconstruction. However, in order to do that, you might be using some sort of a pre-trained model, right? If you actually can see that these are the basically the generated images, um, and this is the whole denoising process. So you are adding noise if you're moving from this, and like kind of denoising. So when during inference you start with some random noise, and then you subsequently add, start to predict uh, a structure out of that, and you'll end up having a image at the end of the whole process. Similarly, you can actually have the interpolation. So this, there are two images in the manifold, right? Like you can see that this is basically looking straight, whereas this is actually looking like slightly tilted face, right? So if you actually do interpolation between them in the denoising space, you can actually end up in a like realistic image. So this is your starting source image. This is your like uh, like the other image, right? Source x0. These are the two images, right? And you start to do the interpolation. You can see that like from tilted you can actually moving toward the straight face, and also you can see that there is a change in the gender, right? So this is from woman, we can actually move toward what you say, a men, and also there's a change in the pose as well. Similarly, in this image also, like we are actually moving from a woman which is actually looking straight, but then toward a different woman who has slightly different pose. Similarly, there's a change in the row 3. There's a change in the skin tone of a person. So we are actually moving from man to a woman, right? Although the pose is slightly same, you can see that the glasses, the attributes of the image are changing. So in this case, like the glasses are being removed, and uh, eventually you are actually closer to your other source image, right? So this is the basically the interpolation step between these 2 points. So there can be multiple uh, sources. So this is source x0, this is source x0 dash, and you're actually interpolating in this space. When you're actually doing the denoising interpolation, you are doing it in along this space. So this is the learned distribution actually, right? So like you can see that like there's a clearly you can say that uh, not only the model learns different modes well, but the space between these two modes is also like some sort of a linear or smooth, right? There is no abrupt changes in um, both of the cases, right? You can see that like here also there is it will start to change the skin tone, and then you can see that like there it has changed it from men to women, and also it has changed the glasses. So this is the basically the interpolation part of the problem. So yeah. Here they are actually showing that like what is the effect of uh, number of steps, right? Suppose you take 0 steps and you start to interpolate, then the interpolation is actually not that good, right? So you want that it you want it to be somewhat uh, in this range, 500 steps range, right? So that like you can actually see that a smooth transition. If it is too high, then at each point you are kind of generating a new sample. So this is what you say, a downside of it. So you want to be in this range, so like maybe 375 to 625 in this range. Also, like if it is slightly lower, then it is better, because it is better in terms of your time computation as well as in your uh, right reconstruction value. And these are actually so this is there's a data set called celeb HQ, high quality celeb images, and I think these are actually generated samples, you can see. So none of them are actually a real celebrity, and all of those samples are actually uh, generated samples, so they don't exist anywhere. But you can see that the quality of the generated images is like pretty good, right? You can see that like all the attributes, you can say that like different, uh, even the backgrounds are different. Like let us see if there is someone is actually wearing some glasses or something. uh, so she is wearing hat, this person is actually wearing glasses. So not only it is generating uh, real look like images, but also generating attributes which um, it's actually a very interesting aspect. Is it making some errors? Let us see. Even if look into this image, you can see that the frame is actually not very correct. So it is making some error. Even in the background, it's slightly weird. Uh, so this is blurred. This is also blurred. Yeah, so the image reconstruction is actually very good, but uh, still there are some cases where like you are actually making some errors. This is unconditional generation for CFAR10. You can see that lot of images are being generated, and these are like very small images. Yeah, so this was the first paper actually, which came up, and the issue was in this case was that like you are actually denoising in the image space, which is challenging. So you require more number of steps, which in many cases become a challenge. So there is one more paper which is called as the stable diffusion, and what they do is they do the whole diffusion process in the latent space. That's why it is called the latent diffusion model as well, right? And like when you are actually using these kind of architectures, you can uh, see that like this, these are actually at the latent space. You have a denoising process actually contains a unit like architectures, right? Your input is actually in the pixel space, right? And then everything actually moves into the latent space. This is also latent space. Each time step is in the latent space. Even the forward and the reverse process happening in the latent space, at the end you have a decoder which basically convert this z into your x tilde, and you can see that like if x tilde and x are basically similar, and x tilde and x are basically in image space, not in the latent space. So this actually helped in many cases where you require less number of steps as well, and also the generation quality of the images is slightly better as compared to what we were expecting in the uh, so this is this also include a conditional variant where you can actually do a text to image synthesis. So so the text is a street sign that reads latent diffusion, and you can see that like it has generated a street sign with latent diffusion. A zombie in the style of Picasso. It has generated image of an animal, half mouse, half octopus, and it has followed the instruction. A painting of squirrel eating a burger. Yeah, so this is what it has generated. So this is a T-shirt with inscription "I love generative model," and it has like faithfully generated. So this actually became to limelight because of this text grounding actually, in the sense that like you can use text information to actually uh, you can actually use text information to generate images. So this is actually very helpful, uh, right? You can see in term of numbers as well, it is like pretty good, right? 5.1 as compared to your VQ GANs, PC GANs, and other diffusion model. So the conditioning in this case can be um like in at a different level as well. So you can actually do the localization based conditioning as well, where you can provide bounding boxes, right? So here what we have done is like we have provided a bounding box which is base flower, concrete wall, and a table. Right? These are the foreground bounding boxes we have provided, and it has generated uh, images corresponding to this is basically vase, this is table, this is flower, and behind is the concrete wall, and that is actually on only in this region. So this is actually pretty interesting. Here you can see that like it has said that like generate a traffic light in this region, and the traffic light is present in most of the images, all of the images, right? You can say that like there are other traffic lights as well. There are cars. So you you are not only generating images, you are localizing them into some extent as well, that like where you actually want to generate. So that is that is actually a very good uh, control. So this is like it is generated a landscape from a segmentation mask, right? Semantic segmentation mask, right? And you can give it as a condition, it will generate the image. Here these are the results for object removal, right? So you have the image and you define what of the object you want to remove, and it it generates the whole image without that object, and these are actually pretty impressive. So this is the painting of Last Supper by Picasso in Picasso style. So these are uh, like very good generation. Also, you can actually use uh, text images, text to generate the images, which actually become additional benefit. You can do super resolution as well. You can see that like you can increase or like create more dimension or give more details to the images as well. So if you actually go to this Hugging Face stable diffusion, so you will end up here. Yeah. So the prompt is generate image of horse running on water, and it has generated images where you can see that like horse is running on water. You can actually see there's a reflection of horse in the water as well. So this is pretty amazing. So let us call set CO and nice. So it actually have the context of unicorn as well, right? And we just changed, but you can see that like this unicorn has three horns. So these are actually good images, but yeah, there can be some more. So you can see that like four legs I can actually see, where the legs supposed to be somewhere here. So this was the prompt I have given. Generate images when you go on running on what, and it has generated these images. Mm. Next in the line is this control net. So uh, like generating controlled images is actually very helpful, right? So what people have tried is, like, suppose if I give you like edge map of a image, can you generate more images out of it? So like any edge detector of this image I'm giving, and it is generating me these images, right? Suppose I am giving you a pose estimation of image, right? And then I want the what you say, my text is chef in the kitchen, right? And it is basically generating the images of a chef in this pose only, right? Like person toward looking toward the right. Similarly, Lincoln statue also looking toward right and also in the same pose. So this is actually like doing the bit here. So this control net actually tells um, that what type of image, like where it basically binds the generation to the localization, where it says that like in what pose or where in what location you want to give generate the images, with a variation given to the text, where you can actually slightly change uh, like what the generated images should look like. So here is the repo for the control net. There are many application, or like many ways you can use it. So you can actually take an image, it will automatically generate what you say, the edge map for that image. You can pass the image to the diffusion model control net, and then it will generate the image of multiple birds, but you can see there is a variation of the color. Similarly, the prompt is basically cute puppy, and you have given the edge map of the puppy here, and it has generated multiple images of the puppy in the same pose. There's a problem of how house interior detection, right? So like uh, what people do is, like, for a given house, you give the edges, and the model actually generate how to actually what can be a changed architecture for the house, right? But while keeping the structure same, right? Like it improve the aesthetics. Similarly for building as well, person as well, oil painting of handsome monument masterpiece. So these are basically in the structure, like taste of oil painting. Cyberpunk. This is from sketch to image. So you can actually draw, scribble something on the paper, uh, put it in the stable diffusion, and it should be able to generate a good image. So this is a sketch which has been fed, and it has generated the turtle, this turtle images, hot balloon image. Similarly, you can actually say dog image you have drawn, and you can just say that like dog in the room is the prompt, and you can see that like in all the cases the dog is actually looking toward the camera. Similarly, like you for a person who's standing in this way, you estimate the pose, and then you give this pose as the input along with the prompt that chef in the kitchen, and it will generate images, like multiple images of chef which is standing in the same pose as the person. Similarly, for this image as well, astronaut on the moon, right, and it has generated image of the astronaut in the same pose. Same for semantic segmentation, depth estimation problem from the depth map as well. They can actually generate images based on 3D map as well. Similarly, anime drawing. These are basically 3D images. You can actually see them in depth as well. Different styles as well. Right, so like you can actually use this to train your data. We are actually working on the same similar problem where we are using this to generate medical images, and the quality of the generated image is actually pretty good. Right, so like the hierarchy is actually in this manner. So first came your diffusion model, which is basically the traditional DDPM models. Then people try to improve the performance, where they say that like why are we actually doing the reconstruction or maybe the denoising process in the image space, let us do it in the latent space. So that like reduce the number of parameters. Also they used this parameter reduction to scale it into a vast data set, right, and using that they are able to actually generate very good images. They tried using text to generate images, which actually become a landmark of generative task, right? And then there is a problem of can we actually do the control generation, where we say that the problem is actually if I say that like the person is should be standing in this position, then the generated images should faithfully follow the prompts or the condition, right? So then it came the control net, where we can actually provide what should be the attributes, what should be the structure, what should be the area, and based on different lines, sketches, some sort of like a rough notation, just to get to generate the good images. So this is what like the the flow of diffusion models was, and you can play with this stable diffusion like a demo, right, and see if you can identify cases where the stable diffusion fails. Then it becomes a challenging or a new research direction altogether in itself, right? So now like we will move toward like what you say, solving few of the questions, and then we will conclude our session. So which of the following represent a valid state transition metric for a Markov process? So for a Markov process, suppose you are you have a probability of 0.5 moving out. You should actually have a probability of zero point 0.5 coming. So the sum of the probability should be actually 1. So this is the condition for this. So we will identify cases where you have the sum is actually coming out to be 1. So in this case, so this is, suppose there are two, right? So first one is basically probability of moving from A to B is basically 0, and then probability of self is basically 1, right? And here the probability of moving this to 1, and this is actually 0, right? So each uh, has a probability of basically, if you sum it, it is basically uh, going out is actually 1. So this is actually a true case in this case, right? So similarly, just sum all the like probabilities. You can see that like uh, this is fine, this is fine, and this is actually greater than 1, right? So that this does not actually hold true. So this turns out to be zero point 0.8, this turns out to be 0.7, so this is also not true. Let us see this case, right? So this is 0.75, this is 0.25, so this is actually true, this is also true, right? So this point, so this is zero point 0.6, this is zero point 0.4, so this is also true, and what do you say, this is zero point 0.6, this is zero point 0.4, and so this combined is actually 1, and this is true. Yep. So A and D are true in this case, right? So the transition matrix, so the probability of going out is actually should be 1 at from any state. Yeah, so we can also say that the row sum is actually 1. So just say that if it is the matrix in this form, the sum has to be actually 1. Similarly, if you actually identify this in form of matrix, if you do the row sum, then is all in all the cases it is. So this is one of the like a trick. So which of the following forward process diffusion kernel will converge to a Gaussian distribution? So in this case, like, so what is happening here is, like, suppose you have an image and you are actually keep on adding the noise, right? And at the end you will have a completely noise vector which is basically a Gaussian, right? So how are we actually adding the noise? So this beta term is basically you're sampling from a Gaussian distribution, and then like you are like adding that noise. So you can see that like you are sampling from a normal distribution which is basically a Gaussian with certain mean and some standard deviation, right? So but like if you are actually sampling from this Poisson distribution or Dirichlet's distribution, you will never going to end up in like converge into a Gaussian distribution. So in this case you have sample A and B will only be able to converge to a Gaussian distribution. Which of the following is true? So DDPM explicitly learn the true function to score concerning the data distribution. Um, this is actually not true, right? So the whole objective is basically to denoise the image, right? So it's, yeah, so it does not actually do anything related to learning the scoring function. So even like it's some sort of a self-supervised itself, right? Like you're basically um, like reconstructing from where you have started. In classifier guided diffusion sampling, one learn the true score function in supervised manner, right? This is also not true, right? Because you already have you basically you don't learn to actually learn any scoring function. You just simply learn to generate samples. Only the condition here is like there is some class associated with whatever sample you're generating. One can usually sample data from images faster than diffusion model. Diffusion model actually takes more time, right? So this is actually correct. Classifier based diffusion model works better than classifier free because the former one enforces explicit supervision where the later one doesn't. So like both of them actually have their own strengths and weaknesses. So there is nothing we can actually say that like if this is one is better than another, right? So in this case only C is correct. Which of the following statement is false? Right? Diffusion model can only generate samples directly from the domain of data itself. This is actually false, I think, because it can generate images. So we have seen that like it has generated images from based on the unicorns as well. However, there are very less chances that the image data where it was trained on should have unicorns in it, right? Like unicorns hardly exist and the data is actually very small. But based on the text information, it has seen that like in text and even in the language model, people have described, suppose there was a unicorn, it looks like in this, it is white, has a horn, right? So that kind of information, when you are actually providing it, that latent space, latent vector actually captures that kind of information and then pass it to generative model. Generic diffusion models can be designed using uh, stochastic differential equation based on the Wiener process. Diffusion model sample based on ancestral sampling in the forward pass. Uh, One learns a score network which predicts the mean of each intermediate function. Let us see, the answers are A, C, D. This one learns a score network which predicts the mean of intermediate distribution. That is, at each step you identify whether we are actually doing correctly or not. Diffusion model samples based on ancestral sampling in the forward process. This is also false. And generic diffusion model process can be designed using stochastic differential equation. This is also false. So next is, in a standard diffusion process, if the data point is initially set to 3 in and the noise variance is at beta, which is fixed at zero point 0.4 at each step, how many steps it would take to approximate the variance of the noise sample to reach 0.9? So we can say that, like, suppose this is the equation of the variance, 1 minus beta to the power of t. T is your time step. Here we just simply put beta is equal to zero point 0.4, right? And if you actually solve it, it is basically coming out to be 1 minus 1 is equal to 0.6 power t. Right. Now you can actually either take maybe log, or just take log and then just simplify it for t. Right, so the answer should be 9. When training diffusion models, does the learning remain invariant to the weight of the reverse process? This is actually false. Learning is not actually invariant to weights of the diffusion process, because at each time step you are actually adding some sort of noise, and your weight decides how you are able to denoise that information. So this is actually a false information, false statement. Yeah. So right, we have some time. Let me just see if I can actually show you the code for. So this is basically the code of stable diffusion. Now there's a earlier there was a version 1. Now there are multiple version, I guess. I have tried training this 2.1 version as well, and like there was a limitation of earlier, that like you can actually train using like to the dimension of 256 cross 256, or maybe 512. 512 now you can actually generate images which are higher in resolution, and like it's basically 768 cross 768, and these are basically high resolution images, so which is interesting. And you should be able to see, you can use these models to basically train, or yeah. So this Hugging Face is one of such libraries which is basically maintaining a lot of diffusion models. So like they are kind of leaders in this way. So if you actually want to train any diffusion model, so they have all the stack of diffusion models. You can actually use pre-trained models, and see if they are working well for your application, if in case you want to generate more data, right? And if in suppose in our case where we were actually working on medical images, even we wanted to generate more data, so the standard diffusion model does not work that well. So what we did is we fine tuned them into our settings, and then we are able to generate more data. So this is useful for data generation task. So this basically is what I was talking about. So stable diffusion and Hugging Face. I'll close the session here. So this is what I have for stable for diffusion based models. Um, I think a good starting point would be to start from the paper and then just see like if you actually want to use them, then you can actually use these kind of models to see where things stand in terms of the generalization of these diffusion model to different tasks, right? So yeah, so I'll close the session here. Thanks everyone for joining. Um, yeah, if you have any doubts, put it in the discussion channel. Yeah, thanks.